Hi, I'm Mahwish Arif, and I'm a PhD student at the University of Cambridge. In this talk, I'm going to present Cinnamon, which is a domain-specific language for binary profiling and monitoring. There are many scenarios where working directly with binaries rather than the source code is either necessary or desirable. One such scenario is when working with legacy programs where the source code is either not available or the recompilation is not feasible. Same is the case with open source libraries or large software, where making modifications directly into the source code is not practical. Similarly, for third-party applications and commercial off-the-shelf software, source code may not be available at all. There are many powerful applications for performing analysis and transformation directly on binaries. They can be roughly divided into three categories. First, the instrumentation could be added into binaries to characterize or profile a program, such as performing code coverage analysis to identify hotspots where a program is spending most amount of time, or detecting bottlenecks, which are slowing down the execution. Secondly, the instrumentation can also be added to monitor the binary execution to either detect the programming bugs, such as use after free, or to protect against security exploits of buffer overflows and return-oriented programming through techniques such as bound checking and control flow integrity. Finally, transformations can be applied on the binary to optimize for different purposes, such as auto-parallelization and optimizing code locality for data center applications. All of these techniques can be implemented using binary analysis and transformation frameworks. These frameworks provide infrastructure support to write custom tools for binary profiling and monitoring, and can operate on a binary either statically, dynamically, or as a combination of both. Static binary frameworks analyze and instrument a binary without having to execute the code first, whereas the dynamic techniques analyze and instrument at runtime. Static techniques have a lower runtime overhead as the instrumentation is done statically. They also have a higher code coverage because they can explore all the possible execution paths. However, the dynamic techniques can recover the control for information more accurately. The low overhead of static techniques allow more complex analysis to be done. However, they are not suitable to analyze shared and dynamically linked libraries. So the static techniques with static frameworks, you instrument and rewrite once and execute the code multiple times. For the dynamic techniques, instrumentation is done every time the code is executed, and so they have a higher runtime overhead. Hybrid frameworks combine the strengths of both static and dynamic techniques. Some of the examples of the static binary frameworks include Tableau, Alto, and Dynans. Similarly, Pin, Dynamo, Ruoyu, and Valgrind are examples of dynamic frameworks. Bitplace and Genus are hybrid static dynamic binary frameworks. Although these frameworks are very powerful, but programming for them is quite a tedious and complex process and is prone to errors. Programmers need to add boilerplate code for each of these frameworks, and they also have to write low-level and complex code to make even simple accesses and modifications to the binary. Here we show an example of to get the memory address being written by a store instruction in two different binary frameworks, Genus, which is a static dynamic hybrid framework, and Dynans in its static rewriting mode. The snapshots show the code to add instrumentation in the binary for every store instruction so that it is further analyzed and the address being written by the instruction is accessed. As you can see that there are significant differences in the way the code is represented in these two frameworks. Also note that there is a lot of low level and complex programming details there. What is needed is actually a programming interface for all different binary frameworks that allows a higher level of abstraction. This is what Cinnamon wants to address. Cinnamon, which is a domain-specific language for binary profiling and monitoring, aims to facilitate programming for these frameworks by providing a higher level abstraction and a more intuitive way of programming. It hides many low-level and complex details which are framework specific and allows the programmer to focus on implementing their specific technique instead of focusing on how to go about doing it. Cinnamon achieves this by offering a number of features. First of all, for the recovery of control flow structure in a binary such as instruction, basic blocks, and functions is fundamental and prerequisite to any static or dynamic binary analysis and transformation technique. Cinnamon abstracts away this control flow recovery mechanism and offers a special types which represent these control flow structures such as instructions, basic blocks, loop, module, and functions. Cinnamon also provides some locations where related to these control flow structures, when instrumentation can be added in the code. These locations may be before and after an instruction, at the entry and exit of a basic block or a function, or initialization or exit of a loop, or there are also some special blocks which allow adding code at the initialization and termination of the program. The code which is instrumented at these locations is called action in Cinnamon. These actions are C++ style statements, and they may include for loops, if-else statements, assignments, and other arithmetic and logical statements. Programmers can also specify constraints or conditions under which to apply certain instrumentation or do certain analysis. Cinnamon also provides different primitive and composite types, as well as offers some new special types. The primitive types include integers, characters, and booleans, where the composite types include dictionaries or maps. There are special operand types, which are memory, registers, and constant. An address is a pointer size variable which can store the address of a memory location or the target address of a control transfer instruction. Cinnamon also defines the opcodes of an instruction, such as call, load, store, return, add, among others. Programmers may also need to access different attributes of a control flow element, such as the name of a function, the target address of a control transfer instruction, or the ID of the loop. Cinnamon provides a very simple interface using a dot operator to access these attributes. To achieve this, we provide some get or accessor-like utility routines that encapsulate the low-level code to access these attributes. This slide shows the code structure of a Cinnamon program, where a programmer can declare some global variables. And the Cinnamon program is composed of a set of commands, and each command executes on a certain control flow element, which in this case, an instruction I, and you can also specify some constraint based on which can work as a filtering criteria for these control flow elements. Programmers can specify any analysis or inspection code, and also the code to be instrumented, which is the actions in this case. So we define here, before I means that we're going to add instrumentation before the instruction I based on certain constraints. There are also special block here, which is an exit block, and the statement within the exit block are executed when the program is terminated. This figure shows the workflow of Cinnamon and its compiler to build a binary profiling on monitoring tool. It has two stages. The first stage involves Cinnamon compiler, which has a front end, and it has different backends for different binary frameworks. The front end performs lexing and parsing on Cinnamon program and generates an abstract syntax tree. The code generator for each backend, for each different target framework, It processes each node of the abstract syntax tree and emits C++ code. This code is categorized as the analysis pass, handler pass, and the interface. The analysis pass is any of the analysis code that has to be done before inserting the instrumentation. The handler pass deals with the adding the instrumentation and calling the instrumentation code. And we have the interface between the two. In the second stage, these analysis pass, handler pass, and interface, they are plugged into the respective frameworks in appropriate places. And then they are compiled using standard compilers. We now present some use cases which can be expressed using Cinnamon. One such use case is instruction counting. And we present two different versions of instruction counting, a basic version and a low overhead version. On the left, for the basic version, you see that the programmer first declares a global variable called instruction count. And then we define a command that operates on a control flow element of type instruction. For each of the instruction, we define some constraint with that the instruction opcode should be the load load. I.opcode is the attribute of the instruction. And for each of the load instruction, we also specify the instrumentation location that before every load instruction, add the code to increment the global instruction counter. And then at the end, when the program exits in the exit block, we print the final instruction count. The low overhead version on the right adds instrumentation for each basic block instead of for each instruction. So we have one global counter instruction count, and for every basic block, there is a local counter, local instruction count. Within a basic block, we analyze all the instructions where the opcode is low and update the local instruction counter. If the local instruction counter for the basic block is greater than 0, then before the block, we add the instrumentation to update the local instruction count and local instruction count into the global instruction count. And then in the exit block, the final instruction count is printed. A second use case is shadow stack, which is used to protect the back edges of a program or to ensure that the return instructions only return to the function that was from where they were called and not jump to any arbitrary location in the code. The code here shows two commands, one which operates on a control flow element, which is an instruction. And for each instruction, it checks whether if the opcode is called. If it's a call instruction, then before the instruction, we add this instrumentation to get the next address of the call instruction, that is where the instruction is going to return, and push that address on a shadow stack. For every return instruction, before the instruction, we add the instrumentation to get the address of the return instruction, the target address of the return instruction, and see whether it matches the address on the top of shadow stack. If it does not, then we report an error. We targeted Cinnamon to 3 different frameworks: Dynast in its static rewriting mode, Pin, which is a dynamic instrumentation framework, and Janus, which is a hybrid static dynamic framework. And we evaluated Cinnamon based on different factors. First of all, we evaluated based on the length of the code to express a certain use case in Cinnamon versus when done directly in 3 different frameworks, which is Dynast, Janus, and Pin. As you can see that the number of instructions to express a use case in Cinnamon is much lower than when done directly into the framework. The second factor is the functionality and portability of the code. For this purpose, we run the instruction counting example on spec CPU benchmark and count the number of load instructions executed by the reported by the program. Please note that this is the same Cinnamon program, which was retargeted to 3 different frameworks. As you can see that the numbers reported by all the 3 frameworks, all of 3 versions, they were very consistent with each other. So it shows that the same Cinnamon program is portable to many different frameworks. And finally, we evaluate the performance of Cinnamon and whether we add any overhead, whether our toolchain adds any overhead. The overhead of the Cinnamon is actually the Cinnamon framework itself. It does not add much overhead to the execution of binary. The main overhead is added by the actual code that is instrumented, and also it depends on the underlying framework. The average overhead that we get was highest for PIN, which is 4.65%. And for Genus and Dynans, it was 1.68 and 0.68% respectively. So to conclude, see that binary frameworks provide powerful means to analyze and transform binaries, but they are difficult to code for and program for. Cinnamon offers a simple interface with more intuitive way of programming to write custom profiling and monitoring tools. We demonstrate through use cases that the abstractions and types provided by Cinnamon can express a range of techniques in a platform-independent way. Moreover, abstracting away low-level details of accessing attributes and control flow elements in Cinnamon can result in reduced code length and complexity for Cinnamon programs. And finally, the same Cinnamon program can be retargeted to different analysis and transformation frameworks that include static, dynamic, and hybrid frameworks. Thank you very much.